very much. Thank you. So I'm sort of glad Italy's slowly coming to an end. I think if I had a single more spoonful of panna cotta, I'd probably explode. I really should start with some apologies before we even get going. Firstly, I'm a little of a fraud. I do not have a first-class honours degree in subatomic physics. And when I asked one of my lighting colleagues who's not here about some subatomic physics, he turned out to have a first-class honours degree from Oxford in subatomic physics, and he knew a lot more than I did, so I'm glad he's not here, because then he won't trip me up. I actually only have an O-level, so that's it. I'd also like to say, sorry, Aidan, there's no questions at the end. So, ruined that for you. You can ask me later. I won't answer it, but you can ask. And then lastly, some plagiarism. I have to apologise to Mr. Rob Halliday, who 8 years ago in Glasgow walked on stage and said, "I'm a lightaholic." Upon which I thought, oh God, yeah, I'm a lightaholic as well. So there's at least two of us. It's a bit of an odd gig to end with. When Declan walked on the stage and he said the words, no pressure then, at the beginning of Showlight, I knew we were kind of like, oh, okay. And he starts to talk about tumble drying some very poorly dyed string. You realise that you're going to be in for quite an exciting Showlight. And we've gone through Grease Live and an extraordinary view into a 3D environment, pie shops. I was very excited about the idea of a pie shop. The politics of doing something in Brazil. Who knew that Sig Cup gave birth to the DOP for James Bond? I was very excited about that. And the terrible hardship, Roger, of doing all those shows in tropical islands. Yeah. If anyone believed a word of it was ever so humid. Yeah, absolutely not a second of it. Puppet lighting. I'm actually going to now go and see a puppet show. I absolutely have to. I thought it was fantastic. Artist-driven projection was exciting. Extraordinary Mickey Kuntu Swan Lake. Candles, yeah, amazing. So I'm sorry, we're going to end with my talk on photons, but at the end of it we get ice cream. So right, let's get going. Right. Photons. They are actually all we see. This is it. There's nothing else. There's only photons. We can talk about fixtures and many other things, but actually, all there is photons. And they are, obviously, if you're going to talk about photons, what you need to do is bring a holiday slide with you. This isn't me on holiday at Tenerife, because I'm obviously behind the camera. The young man in the green T-shirt is my son Alexander, and we're on top of Teide, the observatory on Tenerife. It's Europe's, possibly the world's foremost solar observatory. And obviously we spent most of our time down on the beach drinking beer and things. But in the brief sojourn into scientific study, we went up to Teide and looked through a solar telescope. And you're greeted actually with this. This is what you see. Now, I'm sure you thought this is obviously, it's a photograph of it, but there is something quite magical about seeing the sun through a telescope live. You can really see, you can see the enormity of solar flare, you can see spots. It's extraordinary, and it is photons. It's raw energy pouring from a giant fusion reactor towards you, and it's really quite mesmerizing. So now we get a tiny bit of science bit. Photons are electromagnetic radiation. And the color that we see, be that visible or invisible, be that blue, yellow, infrared, ultraviolet, radio, all of those things, the energy within it is tied to its frequency, how wobbly it is. That's the O-level part of my physics. I'm sure people from Oxbridge have better ways of describing this. And its energetic status is absolutely constant until it's gone. The moment you see it, it has gone. It's been transferred to another form of energy, in this case, chemical energy. But it's finished with. It's lived a long and happy life, probably 8 or 12 minutes, and then gone forever. NASA produced these extraordinary high-def animated movies of their solar observatory. The first time I came across them, I sat and watched this evolving, and just couldn't tear my eyes away from the screen. Obviously, we've coloured this one blue, just because I felt like it, because I like it. So we're going to move on to how the sun works, because I know you all know how all this works, because you're all very, very clever. So we're going to talk about how the sun works. But Ian Dow, he was quite insistent there was some form of experimentation on the stage. He thought that would be a good idea. So I came up with a brilliant idea, and he said there might be health and safety issues. So I said, really, it's just nuclear fusion. How hard can it be? And apparently, were I to be successful, he did suggest not very likely. Then obviously, the side effect would be obviously immediate and imminent death for all of Florence, which apparently that's a bad thing. So instead, I'm going to use lemons. So what's really going on is what we need is we need some lemons. So I've got a bucket of lemons with me. Now, to give you this is the inside of the sun. Lemons. Some sun's gone. It's all right. We'll be okay. Okay. Were this to actually be the inside of the sun, this bucket, it's about 10 litres, would weigh roughly 1.4 tons. The sun is extraordinarily dense, so it's really pretty full of. If I tip this on here, I've got a funny feeling that my colleagues who have changed their travel plans in order to make this lecture, and now sat at the front kind of looking incredulously at me, would be covered in lemons. But so let's pretend for a moment that's the inside of the sun, and it's very, very crowded. So these are the red dots here, the H. So that's lemons, just so that you've all followed along. And it's very crowded, because it's very, very dense. And eventually, you always need to can I shout out to D3, thank you very much for having a mouse mat. Not going to see that again. So what happens is eventually the lemons squish together. These were lemons, but if you get rid of the positive nature of them, that's the tiny little white bit going, and I haven't got anything white, so we're just going to pretend. That we end up with is them squished together, and then we get this. So we now got, anyway, you get the idea. So we've now got what's known as a heavy hydrogen proton atom center. I knew you were excited. Squish this together because it's ever so crowded in here. The level of crowdedness of the lemons is very crowded. So we're going to put that together, and then suddenly these squeeze together, and because they join, they release some energy. So I'm prepared. So the energy that they release that little Y there. Oh, that's not going to work. There we go. No, never mind. The little photon sign is obviously limoncello. So there we are, busy creating this. This is lemons, obviously and limes, representing matter inside the sun, and our limoncello representing, better not, representing the piece of radiation. So this then continues, and we end up with more and more complex things going together, and eventually we end up with a lime-lemon balanced sort of meal, which we can call helium. Now, at this point, this is actually alchemy. We have converted one type of matter to another type of matter inside our sun, and in the meantime, emitted photons. I'm glad I brought the towel. Right. So what does it all mean? There is a European regulation about physics lectures. It's 498 or something. You have to have a picture of Albert Einstein. It's absolutely a requirement that we have an Albert Einstein on screen, which is a little unfortunate, because actually, the person who really thought about atoms for the first time is a Greek guy called Epicurus, about 300 BC. Strange man. He had some very, very, very strange philosophical views about punishment and pain. Very odd person. But he did decide that the world was made of atoms and void, and from it has been the birth of modern subatomic physics in many respects. And obviously Einstein came up with E equals mc squared. Energy equals mass times the speed of light times the speed of light. But to simplify that, energy equals mass times a really big number. That's just the easier way of thinking of it. The important part of that is energy equals mass. Energy, mass. That you can convert one to the other, and theoretically the other way round. We can make mass from energy. We can make energy from mass. Obviously, I've made a mess from lemons. But you do sort of understand that the two are related. That equation says the two are conjoined. We have to mention at this point the duality of energy, of the photon. Is it a particle? Is it a wave? Is it a People at physics parties gather in the kitchen and talk about this all the time. And a very clever man called Schrödinger came up with this concept of particle duality. I won't even start on it. He's really clever. He's way cleverer than me. But he did say that if you opened the box, the cat died. And if you look up Google images on Schrödinger's cat, a lot of dead cats. Like a lot. So I've gone straight for dead alive things. So if those you can read alive, you're basically a positive person, and those who can only see the word dead, you're a bit of a negative person. And if you can only see the word Schrödinger, you're a physicist. We don't do this in our industry. We don't put nuclear fusion at the up at 30 degrees away from the artist. I think it would be a bad thing if that's how we produce light through nuclear fusion. I think it would go poorly for most concerts and TV events. Even film, I suspect, would have a bad time with it. So we convert energy to energy. It's what we do. We take one form of energy, in this case, electrical energy. This is a very early carbon filament lamp. And we use that electrical energy, and we convert it into photonic energy. We convert it, in this case, fairly inefficiently. And our drive has been to make it more and more and more efficient. But nevertheless, we are generating photons. Last science slide, I promise. This is sort of what happens. The energy goes into an atom, be that a tungsten atom, be that a hydrogen atom in this case. We energize an atom. The electron shell expands because it has more energy, it becomes larger. It can't maintain that expansion rate, it falls back. And when it falls back, it generates a photon. Some of the energy is released, and that's the wiggly bit again. We've got more wiggly stuff. So, the wiggly nature of the photon, its fact that it's a piece of electromagnetic radiation with a frequency, we use all the time. This is a bubble. I'm sure you've all seen a peacock feather, silvery blue beetles, all the way through to, full sets of dichroic filters. All utilize the wiggly nature of the photon in order to achieve what you want to achieve. None of this would be possible without the wiggliness. That's a real word. The refractive nature of light, passing through one surface to another surface and changing its angle of incidence, creates lens technology that will work. Without the photon, lenses would not work. We would not be able to push light in one direction, spread it, pull it, soften it, sharpen it. Just wouldn't happen. Absolutely a vital part of our industry is the fact that the photon behaves in certain ways, and we now exploit that for our own uses and our own needs. If you can only see some blobs and there aren't any numbers, if that's all you can see up there, I've got news, you might not be the best lighting designer in the world. I would like you to concentrate briefly on the number 12. This is the eye of my son, Alexander, who we saw at the beginning, staring at the sun. And this is Alexander's eye. He was desperate to pose for this. 17-year-old lad, please can I photograph your eye? Yeah. But it's a picture of his eye. He's profoundly colorblind. On that colorblindness test you just saw, he can see the number 12 and the rest are blobs. He has absolutely no ability to see colors in any normal sense whatsoever. Can I say now that it does make a game of yellow car with him quite interesting. What he describes as yellow can be quite varied. However, he still sees the magic of the photon. He still finds sunsets to be warm and rich and exciting. And he can still go to a concert. David Guetta, for God's sake. and enjoy the visual stimulus. He can absolutely gain pleasure from seeing how food looks on a plate, what a piece of art is, how a photograph looks, whether someone looks nice or not nice, whether something looks healthy or not healthy. He sees all those things. He just doesn't see them the same way I do, or the same way some of you do. And it's led me to think that none of us do. None of us see these things the same way. We're seeing the same thing. We're seeing a photon, and the photon arrives and we process it, and we see this as our own vision upon it. And all we can do is use the magic and use the extraordinary nature of the physics of it in order to excite, entertain, enjoy, bring together all the emotions that you're trying to achieve as designers using the hard physics of the photon. And it's only through that that we realize that we're all actually connected, and that my son's extreme color blindness isn't hampering that enjoyment at all. It's simply different from mine, and I'm delighted to celebrate the difference. So there's the photon. I thank you very much.